So welcome everyone. Today we have an excellent speaker, Professor Juan Banda, who will be presenting. Dr. Banda at his Georgia State University lab, Panacea Lab, works on building machine learning and natural language processing methods that help to generate insights from multimodal large-scale data sources with applications to precision medicine, medical informatics, as well as other domains. His research interests are not limited to structured data. He's also well-versed in extracting terms and clinical concepts from millions of unstructured EHRs and using them to build predictive models like electronic phenotyping and mine them for potential multi-drug interactions, for example, drug safety. Dr. Banda has published over 70 peer-reviewed conference and journal papers and serves as an editorial board member of JAMIA and Frontiers in Medicine, Translational Medicine. He's also a reviewer for JBI, Nature Digital Medicine, Nature Scientific Data, Nature Protocols, PLOS ONE, and several other journals. And prior to being an assistant professor of computer science at Georgia State, Dr. Banda was a postdoctoral scholar, a research scientist at Stanford Center for Biomedical Informatics. And with that, Professor Banda, take it away.
Okay, so let me just start sharing my screen. There we go. Everybody can see this? Yep, good. Okay, so yeah, thanks for the introduction. Most of you know me in person. You've never seen me on video because I don't have a camera. So yeah, so some of you might be familiar with this talk, a little bit of it. I added a bunch of other stuff and newer stuff I've been working on since I presented this for the health equity work group at Odyssey. I'll start again. So yeah, so today I'm going to talk about, seeing if phenotyping algorithms are fair for underrepresented minorities within older adults. This is work that I've done that's funded by NIA through a diversity supplement, and it's work done with Stanford Aging and Ethnogeriatrics, or the SAGE Center, with Vijay Priyakoli and Nigam Shah. So why are we doing this work? Well, we all know how in the last couple of months, well, years now, it's been becoming more and more public that there's all these racial biases in AI algorithms or machine learning algorithms. Anywhere from systems for job searching, for even from image analysis to all these different things that come up. And all the big companies with all the smartest people in the world have these problems, and they're pretty much widespread around everywhere that people are using AI. There's been books about it, more books, even more articles about it. So people are starting to take notice, and there's a lot of people that are doing work on this. This has been work that I'm extending through the phenotyping work that I did, where the main idea behind it is that, well, since machine learning models are biased most of the time, there's few exceptions that aren't, or at least they haven't been publicly shown to be biased. Probabilistic phenotyping models should also reflect this bias. Unfortunately, this is something that people haven't really looked at. Obviously, probabilistic phenotyping it's still not as popular as rule-based one. So here we wanted to create a methodology that could be used in the following settings. So using a standardized CDM, OMOP CDM, that is fully reproducible. So it's part of Aphrodite, where you take your code, you can share it, you can share models, you can share everything, and run it in a different place. And it's fully transparent and configurable. You can pick what models you want, your data splits, data domains that you want to use. I mean, you're not limited to using everything. You can just use a smaller set of data domains, depending if you have EHR or if you have claims data or registry data, etc. So all that stuff it's open. This is not, Aphrodite doesn't produce just black boxes like a lot of the probabilistic phenotyping algorithms out there. The disclaimer here is that we're not trying to find the best performing phenotyping algorithms. We're trying to show if these algorithms are fair to underrepresented minorities, right? So we're just trying to show how much bias they have. At this point in time, I mean, we don't really care if the algorithms, are very good or not. That's something downstream that we look at. So I won't show any traditional model performance metrics. for the models until later in the presentation. I'm just going to talk mostly about, the variance and performance between these models. So the data we use, it's Stanford Health Care Medical Center EHR data up to 2018, converted to OMAP CDM version 5.3. This is around 3 million patients, and the data includes all medication, codes, laboratory records, procedures, and some of the NLP output as well. Phenotyping methodology. So we're using this probabilistic phenotyping via noisy labels through the Aphrodite package, which is built for the Odyssey community. And the big picture of this probabilistic phenotyping via noisy labeling is that instead of using these rule-based definitions like FEAK-AB or the emerged definitions, we want to use the labeling heuristic to identify potential cases and controls and build a model to use based on those patients. This gives you the benefit of, you don't have rigid rules. So in rule-based phenotyping, if the person doesn't fulfill all the conditions, they get dropped out, even though they could be potentially in the phenotype or they're close to getting to the phenotype. But, with rules, unless you fulfill all the laundry list of things, you're out. And with probabilistic phenotypes, you're a certain percentage in or out depending on what thresholds you use. So that's what makes this a little bit different and a little bit more flexible. And the noisy labeling is just the part that it's even better because you don't need a gold standard. You just need a way of labeling this. So let's look at how we starting by, looking at the phenotype data subsets. So we're looking at the phenotype of dementia, frailty, mild cognitive impairment, Alzheimer's disease, and Parkinson's disease. So this is the potential number of cases that we find at Stanford by our labeling heuristic. And this is a potential case. Well, this is the set of controls that I picked. They're all matched by age, gender, sex and race, and duration of record. So here, we can actually see immediately that for race distribution, we're not doing pretty good on, underrepresented races. Obviously, this is a product of, the healthcare system that I'm using the data for. I'm pretty sure if you look at this from other places, it will vary differently. But you can see that there's some representations that are even less than 1%. So we can already start seeing where this can go, where this will be biased, or it's, where we have more data. We also have around 20% of data that we don't know, or it's not specified there under records, what race there is. And that's, fairly standard as well. So the experimental setup that for this work is that, so for the 5 phenotypes, they're all the cases and controls are matched. There's 3 classification algorithms, lasso, random forest, SVM. There's 5 races individually evaluated. And we did 7 mixed evaluations where we looked at traditional models, balanced models, and 1-out combinations. Again, this is going to be described a little bit more in detail further down the slide. So it's around, once you start adding all these things, obviously, that, your number of models that you're trying to check, it's a lot. But, all this automated, all this is, a piece of software that does it for you. So for the evaluation metrics, again, we're going to look at the variance of them. We're not going to look until later on, how the algorithms, the models perform. So for accuracy, sensitivity, specificity, I'm pretty sure everybody here is fairly familiar with it, but I just have definitions there if you're going to glance at them. The important metric that I'm looking at here, is variation. And since we're not fundamental of how the models of the subset perform, we just want to know how different the performance is, because this is going to show how different or how biased they might be towards, different races based on, a wide different set of reasons why, but we'll talk about them later. So the variation is just a comparison between the current model and the base model. So now let's get to the actual results and cool stuff. So there's 2 approaches being evaluated. We build models for individual races and compare across them. And we balance our models and do a leave one out evaluation. So for the individual race evaluation, the steps is we remove all the undefined patients. Yes, it's around 20% of the cohort, But again, you can't use this data with certainty. You can use imputation, you can do other tricks if you want, but we're just trying to, get away from that to add even extra bias or extra noise from that. We separate the phenotype cohorts by race, and we build models for each race and test across them. So it's fairly straightforward. So this plot shows basically the variation of accuracy across the phenotypes for the random forest model. So here, basically the shades of red are showing that the redder, the worse, the less red, the better. And you see a couple of clusters here, or two different phenotypes that are doing pretty okay, where the variation, when you compare one model against the other ones, against the other races, it's not performing that much differently. That's for dementia. That's also for Alzheimer's disease. And you also see some that are just bad in the sense that, you compare the model built, with white patients, with Asian patients, and you take a 7% hit of performance, all the way up to a 25% hit. So once, if you have a model that is performing around 75% accurate, or 75% accurate, and you lose 25% of accuracy, you're back to, flipping coins, which is very bad. And this is exactly where you can see the bias, right? So you can actually see that, if you build a model on a place that has, for example, majority white patients, you at least, by this estimate, you're going to be missing considerable amount of the other patients and the other race categories based on, how different the model performs. So you can see that for frailty, there's a lot of reds. And also for Parkinson's disease, there's a lot of reds. I think that the max they go up to is like 25% difference. But like I said, if assuming the model starts at a 75%, you're basically down to 50% where your model is pretty useless. If we look at sensitivity, right? So we first look at accuracy, now we look at sensitivity. So let's see, again, you kind of have the same clusters, even though this is, also the teaching here is that you also need to look at, across different metrics. Obviously, most people know that, but a lot of people in some papers don't. So if you look at sensitivity, you see that, for example, here, your Native American model is actually not doing that well. For dementia, even though it was fairly stable for accuracy. Alzheimer's disease kind of keeps the same performance. I mean, the variation is actually a little bit higher, but it's still not, extremely considerable. And you see, you see the same patterns across for the other three phenotypes that are, already performing not well. If you look at specificity, again, you have different patterns. Dementia, it's actually showing a little bit weirder patterns and where there's higher variation. And also we have Alzheimer's disease, where you're, doing, I mean, you're performing not as good as the previous ones. So the caveats of this approach is that, analysis are good as your underlying data. I always like to say this, how reliable it is. A lot of EHR doesn't capture race very well. A lot of people shy away from this type of analysis because of it, but it's just, I mean, somebody will take it, somebody will not consider that and just use it, so might as well analyze what happens. Small facial representation will lead to non-generalizable results. That's that's pretty much a duh for a lot of people, but still, it's shown here in the data. The phenotype identification complexity plays a huge role. This is where things start getting interesting, and I'll talk more about this later. And obviously, you need to be aware that when you're doing this type of analysis, you can have a combinatorial explosion if you're adding more metrics, if you're adding more models, if you're adding, even stratifying by ages. So you can get into the hundreds of thousands of experiments depending on how you want to set this up. So now we're looking at that approach. Let's look at, the and the leave one out evaluation. So a lot of people build the models the traditional way, which, you just bank on using as most data as you can, and then just try to, write down on your paper saying, well, as the limitation is that our EHR has mostly blah, blah, blah patients. Therefore, this model might work only for this. If lucky, I mean, a lot of papers starting to do this now, but before people were not even mentioning this. Anyways, so that's the traditional way. If you build a balance where you actually balance the data by equal race distribution or more or less equal, Obviously, if you have one patient from one race, you're not going to build a model with 5 patients and then call it a day. So we did the balancing. We kind of fumble around with the balancing a little bit. So we have models that are somewhat meaningful compared to just, automatically just doing whatever. And also build the models, leaving one out, leaving a single race, because, you will have representation for a few races. So what happens when you just take one out? Let's see. And again, we remove all undefined patients and for the same reasons. So if you see here, this is a little bit harder to look at. But when you see the variation of accuracy across phenotypes for random forest scan, you see that, your full model performed pretty okay. Your balanced model performed pretty okay across races. And obviously your one outs, take different performance hits. So here, if you see in dementia, if you take out the white population, you take over a 20% performance hit, but you can pretty much fully see this. Why? Well, 60% of her data was white patients. Therefore, if you take them out, you have a very weak model that's not going to perform that well. And if you build a model without white patients and test it on white patients, then you have a 25% hit on performance. Alzheimer's disease, this one was actually fairly okay for the fully balanced, full model on the balanced model. And this is what I showed pretty much on the previous slide. Sorry, for the first evaluation. Yeah, and then you see all this other huge amounts of reds, and this is, again, the redder the worse, but you're taking big performance hits. Again, you can go and argue later on that, well, a 12% performance hit, let's say, for frailty, and the model, and the full model with Black people. Well, if you're at 99%, you might afford to take it, but is it really okay to do that where you're actually losing, at least one Black patient, or not missing? You're missing one Black patient, right? So you still need to think about, how to think and how to address those things, or what is your tolerance to, whatever these models are doing. Looking at sensitivity again, we find here we find the stability, across phenotypes. Therefore, this kind of shows that, when you build this full models or the balanced models, they will perform better and more stable than the, individual race models. So, you have at least that. It's a good finding for this. But again, for two phenotypes are doing well, for the other phenotypes, it's not true. So you still have issues. You look at specificity again, you find the same clusters. So at least, we're kind of finding, and we're kind of getting to the, not conclusion, but at least, to a finding that, at least these full models for certain phenotypes are okay, for other phenotypes are still bad. The caveats of this approach, again, you depend on your data, and building balanced models is hard, particularly in institutions with not much diversity. And this is what I was mentioning, that we kind of had to fumble with it a little bit, to, either by using, boosting or other techniques, so we can actually, balance it out without just tossing everybody out, or just have very small models. But luckily, if that's a problem, you can also use other things like federated learning or large data networks, so you can actually, pull from other institutions and get a more balanced model with patients from a bunch of other sides. Again, the combinatorial explosion of analysis it could be an issue here. So what about, the performance? So yes, I know I've given this talk multiple times, and every single time, oh, but how did the algorithms perform? Well, they were not that bad. These models, the individual models for each phenotype, we had a couple of models that, were almost 75% accurate, but most of them, hitting over 90s, again, whatever that means. If we look at Lasso, you have a little bit lower performance. And you also look at SBM, you have a little bit better performance. So again, this is more to round up things, and also for our reviewers for papers. For the approach too, again, you have pretty okay models for the fully, pretty okay performance for the full model and for the balanced model, and some phenotypes. So at least, if you notice, dementia and Alzheimer's disease, which were our more stable phenotypes, the performance is good. So this models is, are at least good enough. I'm just highlighting those, and the same thing for random forest. Oh, I presented the same one. Sorry, that should have been as lasso, and this is the SVM again. So this is just for rounding and to show you that the models are not just doing random picking and then we lose 25% on them, but if we go to the lower end ones and then lose 20% on them, then we are having really terrible models that we shouldn't be using anyways. So the general insights is that, at least for the work with older adults, and I'm going to contrast it with more work that we've done recently. So there's two very stable phenotypes that we found, dementia and Alzheimer's. Since, for both models, the top predictive features are just a handful and they're found in most patients regardless of race. And this is going to resonate a little bit later when I start talking a little bit more in depth about this. The remaining three phenotypes, they showed higher variation due to the fact that, there's almost no dominant features between them. So this is already playing in with the first paragraph. And thus, the models built in each experiment are considerably different. So let's talk about this feature in common. So for the dementia model, on average, out of 7 out of the top 10 predictive features were the same. For the Alzheimer's models, on average, 6 of them were the same. For the frailty models, on average, 2 of the top 10. So you see this huge drop of of features that are representative. Then the frailty model, sorry, I'm going to, oops, there we go. The mild cognitive impairment model, on average, 1 out of the top 10 features are the same. So you can see that, if the top predictive features are different across the models, that your variation is coming from there in a certain way, or at least, that's what we're showing. And for Parkinson's as well, 1. So you see that, for the stable models, we have very common features across. For the non-stable ones, or with higher variations, we have a few. For the big picture findings is that, the main question that we were trying to answer, are these algorithms fair for underrepresented minorities within older adults? Well, it depended on the phenotype and the complexity of the algorithm, and which sometimes has minimal effects. So you find that it depends on the phenotype. So what can we do to improve our models? And this is just the big picture, but I'll talk more in detail about this. So, you do need to have some sort of careful consideration of race distribution on your data, which is the easiest thing that most people do. And you need to do thorough experimentation to assess the performance in the different conditions, which is what a lot of people don't do. And this is what, the package and the tool that we're finishing up will do for you and present you all the analysis, and then you can decide what to do or pick. So does it really depend on the phenotype? So yeah, so I looked at 5. Well, there's a lot more phenotypes, right? And I could have just gotten lucky. Well, we tried the same methodology on 16 other phenotype models, type 2 diabetes, myocardial infarction, AFib, and a bunch of other ones, not necessarily only for older adults. For 10 of those phenotypes, the performance varied widely. It got all the way up to 40% variance in some of them, which is just bad. The theory here for those, at least, was that a wider age range will give you the wider performance variance, and this is what empirically we looked at. However, we need to look into that a little bit more. That was just the first thing that popped out after looking at this other 16 phenotypes. For 6 of those phenotypes, though, the performance was very consistent. There were similar findings, of common features happening on all patients across the race spectrum. So this was not just an artifact of, dementia and Alzheimer's. This was actually something that happens depending on, different phenotypes. So it's not just a fluke. It does happen in other non-older adult necessarily phenotypes. So that, sort of shows that this is a little bit more widespread. So how do we improve these models, right? That's usually what people ask. Well, if you want to tweak model settings to get better overall performance. So this is mostly what I get from, CS people when I give this talk to CSA people. They're like, oh no, but your model is only 79% accuracy. Let's bump it up to 95 and you'll be fine. Well, we tested that. And, obviously the assumption here is that the better the model, the less the bias, right? That's what some people make. This is not my claim. I heard this multiple times, so I put it to the test. This is actually completely wrong. When we tweak, so basically we did a grid search on all the parameters for the random forest, the last one, the SVM, and let it churn out until it found, the most optimal or the best performing model. Well, this actually increased the bias to some of the classes in almost all the cases. So those 20% variations went to, 24, 25, and some of the 25% variations went all the way to 30 and 40% when you had a better model. Well, because it was overfitting, right? So it was overfitting to the highly represented class mostly. And this is just an artifact of, improving the model that is built on top of data that already benefits the class. So that kind of theory for computer scientists was disproven. So fine, balancing race distributions. That's what a lot of people do. That's what most people do in literature or claim to do. Well, yes, this was one of the best approaches to fix the models with common features, though. When the balancing was done in the phenotypes that do not have common features, between the different models, this didn't help at all. And that was what I showed, that the 2 stable phenotypes for the older adults, the 6 stable phenotypes in general, that was the only thing in common they all had, that they had common features. When they don't, even if you balance, you will still not get good models. So that's something that, it's a very interesting finding. So I had this question when I presented at the Health Equity Work Group by Noemi from here from Colombia. And should we just use one model per race then? Well, I don't think so either, because, some of the one single model analysis that we did, showed that there were a lot of performance hits there, or a lot of variation there. And also, this hasn't been really studied across multiple institutions, because the assumption here, I guess, is that, okay, if you build a model at Stanford where 60% of the people are white, build a white people model there, and then run it on another place where it has, less racial distribution for white people, and that should be fine, right? Because it's sort of fine-tuned for white people. Well, and there's no real good answer. Some of the preliminary work that I shown before, it shows that, single race models are not that great. Once you start testing them against different races. However, this to really put nail in the coffin on that, I guess it's more studying that across multiple institutions to have a data-driven answer. So that's something that I haven't been able to look at. I don't have access to 2 data sets, but I've been talking with some people to try to test this out. What about then, so what is the exciting word that came out of this? So I'm a big proponent of that, data-driven initiatives that are pushing in machine learning these days, where, or not data-driven, but, where instead of tweaking the models, you want to tweak the data a little bit. And I don't mean by, changing the data, but tweak, what data you're kind of feeding to the model from your patients. Sorry. So here, the idea is that, okay, let's tweak the features to get better models. It's similar to this anchor and learn approach, but a little bit different in the context that, you're not just using it to anchor and get better people, but you're using it to kind of, find things in common in a data-driven way. So the 50,000-foot level view of what we're doing in this, which is, the next direction that we're following, is that, we're trying to find, or we're finding, this is automatically done, computationally done. So it's not hard, it's just, tricky. So, so you find common features in either the top 100 or the top 1,000 for all models for the badly performing phenotypes, and anchor the models on those features, right? So you can either pick by censoring either domains or either some of the features, or you can give them different weights, so you're actually trying to, level the playing field in terms of, what is the model picking, give it a little bit of better priority for it to build a model that, encompasses all features that are found in all people in all different races, rather than, you just removing them or doing something arbitrarily. So there's a lot of work there. It's a lot of it's iffy, not iffy, but there's a lot of different things to try here. The other thing that, to look at here is that, oh, well, maybe you can use, a clinician or somebody to say, huh, okay, this features sound reasonable. Let's try to pick those features instead. So there's different ways of approaching this. We're just doing it 100% data driven, because a lot of my work is trying to avoid overwork clinicians to give input and to basically guide or rig this to work better. But does this really work? Well, I just found out a couple of days ago that this does stabilize the three older adult phenotypes that perform badly, to less than around an 8% variance, at least for the rats in the random forest. The SVMs need to finish up those. So if we went from 20% variance between models to 8%, that's a little bit more acceptable. I mean, in some, by some definition, I mean, we reduce it by half, which is better than nothing. And this does not have a performance decrease. Well, that's pretty interesting. And that's just exactly what I'm basically working on now. How do we, with the same data, with the same people, how do we try to build a model that, it's basically allowing us to pick for the same phenotype across races in a performant manner. So that's, basically the direction of this is, or the path that this took us to, which, takes us to what's next. I've been getting this manuscript ready for like 7 months now, but I keep following other paths and finding other cool things to look at. So the manuscript should be out at some point by the end of this year, I hope. I'll need to get the package ready for, all the changes tested and deployed. Why? So because, I want to run this at multiple sites. I have a couple collaborators that are interested in running it, but if anybody here is interested in running it at Columbia as well, that'll be great. So I need to have all the software in place, so all of it is done automatically, and you just get to see all the plots and do all the comparisons in person. And obviously, we want to add more of the fairness metrics that are popping up, right? So variation between models is one way of looking at it, but you can look at it from many different aspects with many other different metrics. So what I want to do is basically architect this a little bit better to be able to, incorporate other metrics rather than, just how the models perform differently, which might not be the best way. This is the way that I know how to, and this is the way that I've been hammering at it from that angle. So acknowledgements. This work's been done with Vijay and Nigam at Stanford, and we have the funding for them. So I guess, man, 40 minutes almost exactly according to this. So if you have any questions, comments, feel free to reach out, or I see, so feel free to ask any questions. I'm sorry that I didn't see at the same time the chat questions, because I was just going at the slides. So if you want to ask a question, you can ask it now.
Yeah, so it seems that nobody's asking the questions, so I'll go ahead. So thanks a lot for the presentation. I really enjoyed it. And my question is rather very sort of practical question, I guess. So for those people who are trying to implement some of the models in the clinical settings at the current level of knowledge about the disparities and so on and so forth, what would be the very practical recommendations for them to account for the potential bias? Like my impression was that you want to look at the distribution of races at your institution or at your department or something, and then build a model with a given distribution, and then you have to just live with the fact that some of the people will be underrepresented just because we have like fewer, maybe fewer Asian patients compared to your data or something. So is the recommendation to try to adjust for the distribution of the population that comes to a clinic, or maybe there's something else?
Well, if you want a quick and a quick win, you can definitely do that, and that's shown to work fairly okay. But just like doing calibration, for out of distribution shifts and all this stuff, rerunning this process to recalibrate your models based on more data coming in, this should be something that at least I envision that places that deploy models that are built and tweaked this way will have to do in order to keep their model performant. But yeah, I mean the calibration of distribution of races is probably the easiest quick thing that you can do to at least do okay.
And like a very small follow-up question, but then which was actually the main question that I was leading towards, but like let's imagine we want to establish a new initiative that targets a specific group of patients, let's say African Americans or somebody else, and we don't yet have the data for those patients because they've been coming in not that frequently, but we do want to build a model that will target those populations more because we expect them to come more. Like, what would be the approach here?
Well, yeah, you can do two, right? So you can do, train the model at a different place with the representation of the race that you want, which, Aphrodite allows you to do that. Or you can, if the feature tweaking generalizes, I mean, we showed it to, for 3 phenotypes, I need to show it for the 16 more, and if that does generalize, then it will allow you to build a model in-house, right? I mean, because, I mean, even if you don't have that race, you will still have something powerful enough across the other ones that in theory should work, because I mean you won't have 0 patients, right? You will have some that will guide that model a little bit.
Yeah, the key word here is in theory.
Yes, I know.
Exactly.
Yeah, there's some other hands up. Feel free to talk.
Yeah, if no one else has questions I can ask. Thanks for the talk. That was great. That was very interesting. Can you explain a little bit about the metric you're using, like this variance metric? And also, you showed a lot of these tables with these percentages. Can you explain like what one of those percentages, like what's the interpretation of that?
Sure. Now let me just go back. Oh, the problem with having all those animations is going back. There we go. Yeah. So yes, yeah. So the variance between models is that how much did this model diverge? Each model diverges from your main model or the first model that you built or the best model that you picked. So that percentage will tell you, if one model was, let's assume here that okay, you're losing 10.92%, right? That means that the original model could have been at 90% accuracy, and then this model with 1 Asians, or this evaluation, well, the model built with 1 Asians, was at 90%. And when you only test it against with Asian populations, that performs at 79.08%. So that's the difference there. So the bigger your percentage here is, the more the bigger the variance, the most performance you lost. So I know that the formula, it's this one. Let me just show the formula. Yeah, so it's the absolute value. So you can have the problem of, well, I mean, in theory, you can have the problem that your model is actually performing 28% better, but we empirically looked at that and we saw that that was never the case, that one model was performing better, it was usually performing worse. But I mean, with that metric, and that's why I'm saying that I would like to implement other metrics, is that that could happen. It would be very extremely unlikely to happen, but it could.
Got it. Thanks.
Thanks for presenting. This is great. Really exciting stuff. I'm thinking in terms of phenotyping, there are a few kind of concerns that might influence the robustness of the phenotype, and you touch on a lot of these things. So there's the underlying prevalence of a disease generally, and then within a given group. There are coding practices that might differ among different groups. Some of what you talked about was like common features, so this would play into that as well. Then just generally, there are some diseases that are more challenging to phenotype than others. And so I'm wondering about, if you could talk a little bit more about how these might play into what we're seeing. And then I love that you're on this slide, because my next part is about intersectionality. And, a lot of these tables focus on race specifically. And so I'm wondering, thinking about like Simpson's paradox or something like that, like when you take intersectionality account, do these differences hold across diseases?
Yeah, no, that's a great question. And the problem is that, well, I mean, I guess there is the power to do, N by N phenotypes and, and put an actual answer to all the different diseases, but I don't have the computational power or time to do that. However, I mean, you hit on a great point, right? So based on the complexity of phenotyping, this is a lot, and this is the theory that some of the clinicians that I'm working with have, right? So if it's a harder to phenotype the disease, or based on the coding that some of the the mental disorders are coded very badly sometimes. Based on all of those things, you might be seeing artifacts. That's why we did the analysis with other more traditional phenotypes like type 2 diabetes, MI, these things that are more common, just to see if those patterns appeared again. Because if they didn't appear again, then it was totally some random spurious thing that we just found on the coding of Stanford, right? And that's why, I'm very interested in running this at a different place, just to see if the same phenotypes hold in terms of, the ones that are less varying than others. That I think that would be the best way to show that this, is actually a thing, rather than, it's just a thing found at Stanford.
Hi, I have a question, a follow-up question, Chad, and thanks also for a great talk. Throughout your presentation, you talked about phenotype performance. You talked about phenotypes performing badly. And your metric for that was consistency of phenotype performance across databases. In the questions, we've been talking about the fact that there may be issues upstream of that it may be affecting your phenotyping, information loss from the unstructured to structured data, overlapping clinical presentation of some of these illnesses. And so my question for you is, involved in your phenotype performance metrics, is there anything that measures loss from the source?
That's a great question. And that's something that I didn't add here, but we have a plot basically of, we have the same plot, but removing every single domain. But you can imagine how many more plots would I have to show to actually show all of them. But in general, if we remove the NLP, we lost on the overall performance of the algorithm, around 3%, 4%. If we remove codes, for most phenotypes, the performance was huge. So there are ways in this package that once it's released, we'll have an option of, allowing you to turn things on and off to look at that. But, based on just the massive amount of more analysis that I would have had to show for account through all of that, I basically removed them from my presentation. But yeah, you touch on a very interesting thing. And also, the performance drop by removing certain domains or certain data types, data availability types, you will, it varies between phenotypes as well. So it's a question that leads to way too many more questions.
Okay, well, Professor Banda, if there are no other questions, I want to thank you for your time. This is some great research and overlaps with a lot of our interests. And if anyone wants to follow up, we are happy to share Dr. Banda's contact information again. And thank you so much.
No problem. Thank you for having me. And feel free to reach out if you're interested in any of this stuff.
Have a good day, everyone.
Thanks. Have a good day.
Thanks.